So, so the test is on Thursday. Where somebody asked about where the review was. So if you go to Blackboard under course content, and if you go all the way down to the bottom, it says test reviews. So if you click on that, you'll see Chapter 10 test review right there. So like I said, I think I said before sometimes it's 49 minutes long, so I do go into a lot of detail on what kind of problems to expect on the test. Because your class is ahead of the other class, I'm going to have it so that on Thursday all we're going to do is take the test. So we'll come. So at 10 o'clock we'll start the test. It's meant for a 50-minute class, so you should have plenty of time to get it done. Okay, so if everybody can stop talking, please. So I don't know how this class got so far ahead of the other class, but that's the way it is. So we were talking about probability last time. We talked about theoretical probability for things like flipping coins. Now today I'm recording the class. Actually, I'm recording it because Allison's sick, so I decided I'd just go ahead and record it. So we're talking about probability. So theoretical probability is things like flipping coins, rolling dice, card hands. And then there are experimental probabilities, which are things like, I guess, anything that would be determined from experiments. So yesterday I decided I was going to go check my experimental free throw probability. So I practice my free throw shooting. And so I'm going to show you my results here in a second. So what I did was I shot 5 shots, and I recorded how many I made. And then I shot 5 more shots, recorded how many I made. So I was trying to develop a kind of theoretical probability of me shooting free throws. I might turn them down a little bit. So anyway, here's the results. That's not the results. Open. Basketball percentage. Okay. So this is just to show you how you would analyze something like this. So what I did is I made up this. These are the total number of shots I'd taken, and for each 5 shots, these are how many I've made. This was the percentage for each 5 shots. And then what I did is I did a running average. So what that basically was for the first 5, it was the average for the first 5 shots. And for the second 5, I took all 10 shots and averaged those together. And then when I took the next 5 shots, I averaged 15 together. So these numbers are always going to be 20, 40, 60, 80, or 100% because I only shot 5. These are based on 5 shots. This was my running average. Now, here's a little background. I shot a few baskets at Thanksgiving because my daughter's family, my daughter's son-in-law's family has this Thanksgiving get-together, and the person who has the party has an indoor basketball court at their house. It's a half-court indoor basketball court. It's like 2 stories of a house, and so I shot a few shots then. And then last spring, I had a student in my class who played basketball at Allegheny, which Elena Fridley, and I was going to challenge her to free throw shooting one time. She was in the governor's school, and so I shot a little bit just to get a little practice. So that was about a year ago. So I've shot twice in the last year. So as you can see, I kind of started off a little rough. So the first 5 shots I got 60%, then I got 80, 80, 40, 80, and so forth and so on. So the running average, you can see, starts out in the 70s, and ultimately when I finish, I was shooting an average of 80%. Now, also what I did was I took the last 25 shots and averaged those together. So I was getting better as time went along, which you would expect. There was actually about a point where I saw a shift. So I must have gotten, my brain must have connected to my hands. So by the time I was finishing, I was shooting 92%, 96%. So that's pretty good. So here's my graphs. Here's my data. So let's check out the results here. So this curve is the running average, and you can see. So this is based on, I think I shot 155 shots, 155 three throws, and so this number here is I shot out of the 155 three throws, I shot 80%. I started off kind of low, and then I got better. And then if you took the average of the previous 25. So the first 25 shots, I averaged 68%. Then the next 5 through 30, which is 25, I averaged 76%. And you can see by the end here, you can see where my brain connected to my hand, about right here. So that was after 95 shots. So after 95 shots, I got much better. And then I averaged around 88 to 90%. So I didn't make that up. So I'd shoot 5 shots, I'd go write the number down. Shoot 5 more shots, write the number down. So I didn't. That's kind of the process. So this is kind of the law of large numbers. You know, I think I would actually probably start from here because the first 100 was the fact I hadn't shot for a year. But you know, it levels out at this point at some value, and that I would consider that to be my long-term practiced free throw probability would be somewhere between about 90%. Okay, so now if I went over there today and I had to practice a little bit, I wouldn't have to practice so much because my brain's connected to my hand. I'd expect long-term average would be about 90%. Okay, so let's continue on. Now the reason that 90% is pretty good, considering my eyes. I'm going to tell you my eye story. I don't think I told you guys my eye story before. So up until about 6 years ago, I had normal vision, and we were going on a trip to Maine. So we stopped in New York to visit my daughter, and when I got out of the car, I felt kind of dizzy and thought, well, that's weird. Wonder what's going on. So I figured just driving 8 hours was the problem. So we went to her apartment. I said, I think I'm going to lay down. I don't feel quite right. I feel kind of tired. So I got up, and yeah, I could see. One thing I noticed, not exactly that time, but the next time I laid down, that when I laid on one side, everything looked fine, and when I laid my head on the other side, I had more than one image. I thought, that's kind of weird. Okay. But sometimes you have things happen to you, you ignore them, they go away, and you never know why they happen. So, well, to make a long story short, we went to Maine, and we were camping, and the campground it didn't get any better. And if I tilted my head this way, it was okay. If I tilted my head this way, it wasn't okay. So I went to the campground, had like Wi-Fi in the laundry room, so I went to the laundry room, got my computer. I hadn't told my wife yet, so I searched for double vision with head tilt. And it came up with this thing called fourth nerve cranial palsy, which is when one of your nerves from your brain to your eye muscles gets damaged somehow. And it said, if you have this, you should immediately see a doctor. I'm like, okay. So that was, we cut our vacation short, drove to Winchester, where my family's from, and went to the emergency room. And they did a MRI, and what they were looking for was an aneurysm or a tumor. Okay, both bad things, right? So I was ready to be told I had a brain tumor. I convinced myself that I had a brain tumor. So anyway, I talked to the neurologist, and she says, "Well, we looked at your, MRI, and we don't see anything. Well, we see something. It's your brain, but we don't see anything wrong with your brain. You don't have a brain tumor, and you don't have an aneurysm, but we don't know what. And we think you have fourth nerve cranial palsy." But we're going to want to make an appointment with an ophthalmologist so he can look at you. So we go to an ophthalmologist, and the ophthalmologist says, yeah, you've got double vision with head tilt, and you probably have fourth nerve cranial palsy, but we need to send you to a neuro-ophthalmologist at UVA. Okay, so we made an appointment for a month later. Went to the neuro-ophthalmologist. He did all these tests. He said, yep, you've got fourth nerve cranial palsy. We don't know why, but you do. And so you can either have surgery or you can have glasses that have prisms in it. So that's what I have. And so if I take my glasses off and I don't use if I see two images I see people's heads about this far vertically displaced. And that's because this eye is not tracking the same as the right eye. And so I have two eyes. So when I wear my glasses, I can see okay, but peripheral vision is awful, and looking down is not so good either. So playing basketball is pretty much out of the question because you need quick peripheral vision. But the free throw shooting, that's really, there you can look. So I'm dribbling the ball, practicing, and I can't see the ball that well. So that's not too good. But once I have the ball and I look up at the basket and I shoot, boom, then I can still do that. So that's my one thing I can still do. Shoot free throws. Pretty decently. Okay. So we were talking about, I think we might have mentioned this, but probability is the number of favorable events divided by the number of events in the sample space. So for example, free throw shooting, the number of favorable events, or making them, the number of events in the sample space is how many I take. Now, odds uses that same information, but in a slightly different way. So it says here, if the probability of an event occurring is A over B, favorable to total, then the odds in favor of the event are A to B minus A. So let's use basketball free throw shooting here again. So let's say I make 8 out of 10. So the probability of making a free throw is 8 over 10. We could say it's 4 divided by 5 if we simplified it. So that's the probability. The odds would be 4 to 5 minus 4, or 4 to 1. So that's good odds. When this number is greater than that number, you're better than 50% chance of something happening. So that's the odds. That's the odds for, or in favor. If I wanted to do the odds against, so odds against making a free throw would be 1 to 4. So you just switched places. Odds for, 4 to 1. Odds against, 1 to 4. The probability of not E, meaning the probability of me not making a free throw, is going to be 1 minus 4/5 or 1/5. Actually, we'll talk about this in the next section, but the probability for an event plus the probability for not an event is always 1, because it's either going to happen or it's not going to happen. So there's this other second thing. If the odds in favor of event E are A to B, then the probability of the event is A over B plus A. So let's look at that example. So let's say, looking at this is case 1, where we're given the probability. Case 2 is I'm given the odds, and then I calculate the probability. So let's say the odds in favor of event E is 5 to 4. What is the probability? For event E occurring. So in this case, the A and B are referring to different things. So in this case, A is equal to 5 and B is equal to 4. A is the first part of the odds and B is the second part of the odds. So it says if the odds in favor of E are A to B, then the probability of event E happening, so the probability is going to be equal to A over A plus B. So all we do is just plug in the numbers. So it's 5 over 5 plus 4, or a probability of 5/9. So you can see what you can do is you take the first number in the odds, put that in the numerator, and then add the two numbers involved in odds. That's your denominator. So that's converting from odds to probability. If you have probability, you take the number in the numerator first, and you have odds to B. B is going to be the difference. And since the denominator in probability is always greater than the numerator, you're always going to get a positive number. So if I went from a probability of 5/9, I would take 5 to 9 minus 5, which is 4. And a lot of times I'll ask on not this test, the next test. When I ask about probability, I'll ask for both odds and probability. Usually you calculate probability first and then calculate odds using this formula. Okay, so we're going to do just a simple probability and odds question here. So this says 5 people, Alan, Bill, Kathy, David, and Evelyn, form a club. It's called the N Club here. And it consists of the 5 people. Those just represent them. If you choose a president randomly, find the odds against each of the results and the probability for each result. So it's really easier. If they ask you for the probability against, it's probably easier just to do the probability for, and then you just take 1 minus the probability for to get the probability against. So that's what I'm going to do. I'm not going to answer the question directly. I'm going to answer the probability for and then figure out the probability against. So the probability for picking Kathy, and then the probability for not picking Kathy, the probability for picking a woman, and then probability for not picking a woman, and the probability for picking a person whose names begin with a constant, and then I'm going to answer the question, the probability against picking somebody whose name begins with a constant. So let me add a page here. So here we go. So part A. So remember, the probability of an event occurring, or the probability for an event occurring, is going to be equal to the number of favorable divided by the number in the sample space. Now for all of these, the number in the sample space, which we use n of s, is going to be 5, because there are always 5 people. What's going to change is what is the numerator. So we just have to decide what is favorable relative to each part. Well, favorable in case of part A is Kathy. So how many Kathys are there? Okay, so in this case, the number of favorable events, there's 1, because there's only 1 Kathy. Therefore, we can use those two to calculate the probability for event is going to be 1 divided by 5. So that's for event E. So if I want to find the probability, so I'm actually starting with probability because that's easiest. Okay. So the probability for event E occurring is 1/5. The probability for not E, meaning not Kathy, is going to be equal to 1 minus the probability for Kathy. So you get 4/5. So that's the 4/5 is the probability against event E, which is Kathy, picking Kathy. So once we have the probabilities, the odds are easy. So we could say the odds for picking Kathy is going to be equal to, well, you take 1, the numerator, to the denominator minus the numerator. And you can do this in your head. I'm just writing it out. I would not normally write it out here. I just go straight to this part. So the odds of picking Kathy are 1 to 4, and therefore the odds against. So you can actually get the odds against either by taking the probability against, or you can just switch them. So the odds against picking Kathy are going to be 4 to 1. So you can either just switch the two, or you could see that if I use the probability, I'd take 4 to 5 minus 4, which is 1. So this, you can switch. There's the switch approach, or there's the formula approach, which would be 4 to 5 minus 4. So that's the formula. You still get the same answer, 4 to 1. So let's see if you can think about the next one. So I'm going to put this back up here. So let's go with a woman. So the first thing you're going to do is, what's the probability of picking a woman? So I'm going to, you figure out what that is, and I'll ask somebody the question. So we're going to go to B. Oh, it did? Yeah, I must have bumped the cable. Okay, so the first thing we're going to do is we want to know what the probability of picking a woman is. So I'm going to just put as probability of woman. So here we had 1 Kathy out of 5 people. So all you have to do is figure out how many women we have out of 5 people. So let me ask somebody here. How about Victoria? So what do you think the probability of picking a woman would be? Well, the number of women is 2 divided by 5. Yeah, so the probability is 2/5. Okay, so the probability of against picking a woman. So that's somebody over in Rockbridge. Okay, let's see. So yeah, my mind's going blank here. Haley, Truslow, what's the probability against picking a woman? Remember what we did? Pardon me? I heard something. I think you got it right. Say it again. Yep, 3/5. 3/5. Yeah, that's equal to 1 minus 2/5. Okay, so that's that. So let's do the odds for, we'll come back over here, for picking a woman. So let me see here. Amaya. So what do we do? Remember what the formula is? So here was the odds for picking Kathy. So you take the numerator. Anyway, do you have an answer? I don't want to answer it for you if you have an answer. Okay. So the first number in the is going to be the numerator. So what's the numerator of the probability for picking a woman? 2. So it's going to be 2, and then I took the denominator and subtracted the numerator. So what do I get if I take the denominator and subtract the 5 minus 2, which is 3. So the odds for picking a woman are going to be 2 to 3, and the odds against So we'll go back over to Rockbridge here. So Kelvin back there. So what do you think the odds against picking a woman are? So what did I do here?
32.
Yep. So all you do is switch them. 3 to 2. Okay. That's it. Okay. Not so hard. Okay, so let's go to do the next one. We'll leave this one up. We'll add another page. So part C is for a person whose name begins with a consonant. So, consonants, remember, are not vowels. So Bill, Kathy, and David, they all start with a consonant. So the probability for picking a person whose name starts with a consonant, I don't even know how to spell. How do you spell consonant? Consonant. Okay, so we'll do that. We'll see if you can figure them all out before we go through. So then there's the probability against. We need the odds for and the odds against. And whoever I ask, I'm going to ask you all these questions. So I'll give you a minute to answer these questions. So don't wait. Don't do the first one and then wait. I want you to do all of them. And you can look over at the left-hand side to help you out. In this case, the favorable event is the names who start with a consonant. And it's going to be somebody in Rockbridge. So okay, so I'm going to ask Madison Alston in the back row there. So Madison, what are the answers?
All right, so probability for it.
Yep. Okay.
Against is 2 over 5.
Yep.
And the odds for it are 3 to 2. And then the odds against are 2, just 3.
Okay. So that's good. So again, favorable outcomes, we have 3 of them. We have 5 total people. So 3/5. Here you have 1 minus 2/5. 1 minus 3/5 gives you the against. 3/5 plus 2/5 equals 1. 3 is the first number. 5 minus 3 is the second number. For the odds and for against, you just switch. You switch because against becomes 4 and 4 becomes against as far as those two numbers. Okay, so that's pretty easy. Okay, so the next two things I'm going to talk about are where probability is useful. So I have life insurance and I have something to do with retirement. So here's my little example. So let's say we'll talk about this later in the semester, but people buy life insurance. Why do people buy life insurance? Because there's two kinds of life insurance. There's what's called term life insurance, and there's something called whole life insurance. Term life insurance is basically if you die, your beneficiaries get X amount, and whole life insurance is more like a savings. So if you die, even if you don't die, you can sometimes cash in your insurance as kind of like a savings thing. So we're talking about term life insurance. So when I was a lot of places you work, you get as a benefit so many times your salary as life insurance. So here where I work, and this is any state employee, you get twice your annual salary for life insurance. And it doesn't matter whether you're 22 or 65, you still get twice your annual salary. Which is nice because when you get older, as I'll point out, life insurance costs more because you're more likely to die during that period of time. So when I was probably 40-ish, maybe 45, maybe it was 45. I don't remember exactly. It was in my 40s. I decided to buy a reasonable amount of life insurance. So here's the facts. So I bought $500,000 worth of life insurance. And the cost, you see these commercials, you can get blah, blah, blah for blah, blah, blah. So it cost me $45 per month, which is how much per year? It's going to be about $500 and some per year. And the reason I bought it is because I don't think at that time my kids had graduated from college. So if I died, then there would be money to send them to college, and I think we'd paid off our house, so that wasn't an issue. But so I'm paying $540 per year, and if I die during that year, my beneficiaries get the money. So the question is, if you're the insurance company, you need some information. What is the probability of somebody who's 40 years old dying in a 12-month period? And in this case, a lot of times these insurance policies are good for a certain amount of time. So this was a 10-year policy, so I paid the same amount every month whether I was 40 or 50. So you kind of have to do some kind of an average thing, because people who are 50 are more likely to be dead than people. People said this is a morbid discussion, but it's reality. So you're less likely at 40 to die than at 50. Okay, less things to go wrong with you. So what the life insurance company has to do is has to make sure that the probability of somebody dying with certain health conditions doesn't make them go broke over the long run. So they take statistics for basically doing experimental probability or empirical probability, and then they figure out how much do I need to charge somebody every year so that I still make money over the long run. So you can kind of figure out, based on this information, you can figure out what the chances are of somebody dying between 40 and 50 years old, which is kind of an interesting fact. So the way you do that is that you take the total amount of life insurance you have and you divide by the amount per year, $540. So if I take 500,000 and divide by 540, I get 926. So what that means is basically if you had 927 people, you get enough from 927 people paying $540 a year so that you could pay off one person dying. Okay, so you'd say, here's my income. If you were the insurance company, your income would be $540 times 927 people. Say, I'm going to increase it by 1. So 540 times 927, and I get 500,000 and 580. Okay, so that's how much money I bring in, and the the cost is if you have one person die and they get $500,000, you get that, then you're out $500,000, and so your net income for that year is $580. Well, obviously that's not a good business proposition, because if you're only making $580 a year insuring 927 people, it's not going to be, it's not great business. At least you'd break even. So this is kind of a worst case scenario. So how do you relate that to probability? Well, you would just take 1 divided by 927. This is, approximate. 927. So what do we get? 1 divided by 927 equals 0.0011, or 0.11%. So that's kind of the upper limit on mortality. It's got to be less than that, or the insurance company is not going to make any decent money. They are going to have the money to invest it, but that's you're not going to make a huge amount every year. So that makes you feel pretty good. If you're 40 years old, you have probably less than 0.1% chance of dying. Okay. Now here's the bad news. Okay. Let's say this was from 40 to 50 years old. It might have been 55, but let's say it just make it up. So I'm going to assume 50. So when I got my insurance policy, this is for 50 to 60 years old. So you would sign a new contract that would say from 50 to 60, you're going to pay this much per month to get in $500,000 insurance. So when I got I decided not to do it because it turned out that the price went from $45 a month to $450 per month. So that would mean I'd have to pay $5,400 per year for the same insurance. Well, $540, yeah, I can handle that. $5,400, I don't know about that. It's kind of like with car insurance. At some point, if your car's old enough, the value of the car is low enough that even if you have the car is totaled, you might only get $1,000 for your car. That's probably my car right now. I have a 2000 Honda Accord. The trade-in value is $500. I haven't done it yet because I'm stupid, but it still has collision. So if I wreck my car, I got $1,000. I can buy somebody else's 2000 Accord, maybe. So you make those decisions. Here, I did it with the life insurance. But also what that means is that the probability of dying in this age range is probably around 1% instead of 0.1%. It's still small, but it's definitely more significant. So where's probability used? If you work for an insurance company and you're trying to figure out the rates for charging people for any kind of insurance, you'd have to take the data, which is the empirical probability, and then use that data to decide how much to charge people. If you don't, you want your insurance costs to be low, but if the company can't make any money, then they may go bust, and then you don't have any insurance. Okay, so that's kind of. And this actually kind of has the same, uses the same kind of data, but it's another way of looking at it. So here's what's the probability of dying? 1. Okay. No matter who you are, what your age is, at some point that's going to happen. Okay. Anyway, minimum required distribution. So this is if you invest in tax-deferred investments like IRAs or 401ks, which we'll talk about in more detail later. But they're just ways that you can put money in a savings account and not pay tax on that money initially, and the tax is deferred. But at some point, the government wants some money. So whether it's a traditional IRA, a Roth IRA, a 401k, when you reach the age of 70 and a half, you have to start taking the money. You can't just leave it in there till you're 90 and then leave it to your heirs. They want you to at least start taking some amount of money. Now, they don't ask you to take all the money at one time. So it's not like you turn 70 and a half, I've got to cash in this IRA for $100,000 or something like that. But they do require that you take a certain amount per year. So here's my example. My mother left, when she died, she left some money in terms of an IRA to each one of her sons, 3 sons. And because she was already over 70, she was being required to take a certain amount per year, whether she wanted to or not. And it turns out if you're an heir, you also have to take a certain amount per year, and it's dependent upon your lifespan at a particular age. And so they have these tables that tell you what your lifespan is based upon if you've made it to 60. So, it's kind of an interesting thing. If you look at the average lifespan of a male in the United States, let's look it up online, see what it says. Everything's in Google these days. So lifespan USA, male. Okay, so the average lifespan for a male in 2015 was 78.7 years. So then the question is, I'm 60 now. So does that mean I have, on average, 18 years left to live? Well, the answer is no. I actually have, if you make it to 60, you actually have more time to live than if you, using just the lifespan kind of thing. So if I go to the internet here again, and I look under minimum distribution tables. Okay. Actually, I was, just a second here, inherited IRA. Okay, so here's the table that you would use. So you're inheriting, and what is minimum? Okay, so where's the table? And okay, so there's a table somewhere. Let me find the table. So this is the this website bankrate.com. So here's the information. Let's look at it. So if you're 70 years old, they decide that they're going to give you 127.4th, okay, 127th of the amount. So if you had $100,000 in your account at 70 and a half, you would have to take, what you do is you divide 100,000 by the average number of years you have left to live here. So you would have to take $3,649. So your bank account will be lower. Now the next year, when you turn 71, your distribution period in years gets reduced. But even if you're 100, it's still saying you have 6 years left to take the distribution. Okay, so so the thing is, if you have a 90-year-old grandmother or great grandmother, you might think, well, they're way past their lifespan. But on average, they somebody who makes it to 90 years old, the average person who's 90 actually is going to make it to 95 or something like that. So from my perspective, since I'm getting old and you guys, I'm thinking about it, you're not thinking about it. The reality is that since I've made it to 60, I think the average lifespan for somebody who's already made it to 60 is something like 82 years. So I've got 22 years. I just got another 5 years or 4 years. Woohoo! That's exciting. Okay. Okay, back, moving away from morbid stuff. So these are just some word problems that we're going to determine what the probability is. In this case, they're empirical probability, like my free throw shooting. There's an experiment they ran. The question, what you would use this data for is you'd say, okay, now if I now plant 10 additional seeds, what's the probability of me getting 5 of them to germinate, 6 of them to germinate, 7 of them to germinate? We'll answer that question, but right now we're going to say, what's the average probability? What's the most likely result that I'll get? And you can use that with the empirical probability. So it's real simple. This is problem 14. You've run this experiment. You've planted 200 seeds, so that's my sample space. I've got 175 of them germinated, which means they can grow into plants. Find the empirical probability that any particular seed of this type will germinate. So now that I've run this experiment, I have this empirical probability. And all it is just the number of favorable events divided by the total number of events. And I can simplify this down to 7/8. So that's the probability of any, now taking any of these kinds of seeds, planting them. If I plant, a whole acre of seeds, on average, 87, this comes out to be 0.875, so about 88% of them are going to germinate. Okay, next one, 16. So what's the probability of having 2 daughters among 4 children? And this is kind of like flipping a coin, because when you have, for the most part, we're going to assume that it's equally likely. It's not exactly equally likely. What's the latest percentage of live births? I think it's males more than females. Is that right? Let's check that out. So let's say percent sex. That's a dangerous thing to put in here for live births. Sex ratio. Okay, there we go. Percent preterm live births. Percent. No, that's not telling me the answer. Human sex ratio. There we go. Huh, that's an interesting picture. Let's look at that. Countries with more females than males. Countries with the same number of males and females. Countries with more males than females. So the U.S., Canada, Europe, Soviet Union, former Soviet Union. So then you have these where you have more males. Now China, there's that the Chinese place, and maybe a lot of the Asian societies place more value on male children for whatever reason. Well, we know why, but it's not a good reason. But anyway, so that's not surprising. It's also interesting through this area, which you would consider to be more Islamic. That's my, I'm trying to find a reason why this is the thing. Now, why Iceland is it? That's another question. Who knows why? Or Norway. So if it's really cold, then it's more likely to have a male. So that's interesting. You can think of all kinds of reasons about that. So apparently if it's really cold, it's more likely to have males. And then you have green here. So that's more equatorial. Anyway, so there you go. Let's see if we get. So you learn all kind of new stuff here you didn't know about. You thought it was just a math class. For mothers having their first baby, the total sex ratio at birth was 1.06 overall, which I'm assuming is more females than males, maybe. The age of the mother affected the ratio. Anyway, I have to read that. That sounds interesting. Anyway, here's our problem. So we're assuming here that it's 50-50 chance. So if Kathy here has 4 children, what is the probability that she will have exactly 2 daughters? So all you have to do is figure out what the sample space is. In this case, the sample space is not done experimentally. It's going to be done theoretically. And you could use a tree diagram, but I'm just going to write out the possibilities. And so it's like heads and tails tables, but it's going to be male and female. So if we draw, what I'm going to do is we're going to have 16 different possibilities, because you have 2 to the 4th power. 2 choices times 2 choices times 2 choices times 2 choices. Okay, So while I'm talking here, I better not get carried away. So the first child can be half a chance that it's a male, half the chance it's a female. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Then what we're going to do is we're going to do 4 in a row of male, 4 in a row of female, 4 in a row of male. So that's the next step in this logical approach. This is what I'm doing now is systematic listing. Okay. So then I'm going to do 2 males and 2 females, and then I'll alternate them. So I should probably do this instead of talking so I don't make a mistake. So this is one way of coming up with the possibilities. We remember we did that with flipping a coin. So I'm gonna tell you the results. You can verify it by looking at this at some point. So if I went in there, what I'd find is no girls. Out of this, there's 16 possibilities. No girls, 1 girl, 2 girls, 3 girls, 4 girls. So there's 1 possibility with no girls. That's all boys. There are 4 possibilities with 1 girl. That's basically the 1 girl gets stuck a different this one, and that one. Then there are 6 with 2 girls or 2 boys. 3 girls or 1 boy. There's 4, and 4 girls. There's 1. And should look kind of familiar. This is 4 things taken 0 at a time. This is 4 things taken 1 at a time. This is 4 things taken 2 at a time. 4 things taken 3 at a time. 4 things taken 4 times. These are all different ways of figuring out what the answer is. Because the sample space n of s is 16. How do I know that? Like I said, you can take there are 4 parts to this process. So 2 to the 4th power, or 2 times 2 times 2 times 2 times 2 is 16. So I know the total is 16. I could also add these numbers together, which add up to 16, or I could count all of these, which add up to 16. So there's all different ways of getting the number of choices in the sample space. To answer their specific question, the favorable event is having 2 daughters. So the number of favorable events is going to be 6. So the probability of having 2 girls and 2 boys is going to be 6 divided by 16, which is 3 divided by 8. So it's not quite 50% chance. A little less than 50% chance. So how many people would say boys run in their family? Anybody agree with that? Okay. How many people say girls run in their family? Yeah. And that's based on your particular experience, because you are probably one of these, where you've had 3 girls out of 4 or 4 girls, or you don't have to have 4 children for this to, you've had that experience. The question is that really true or not? That's kind of in our family, my brother's wife had 2 girls. Well, no, he had a girl and a boy. We had 2 girls. My other brother had 2 girls. So 5 out of 6 of our generation were girls. So you might think, oh, girls are in the family. But the previous generation, my wife, for example, my wife had 2 brothers. I had 2 brothers. So 5 out of 6 were boys. So, is that, so now you're saying, does it alternate between generations, or is it just one of those things that happens randomly and you've observed it, so you think, oh yeah, that happens or not? So how many people think that actually happens? Do you think girls run in families, boys run in families, or is it just There just happened to be one of those lower probability cases. Because of what? Two people vote. There weren't that many people who raised their hands that said that. So so here's the question for Google. It's amazing what Google will do for you. Okay. Do girls or boys run in families? Somebody's probably done some research on this. And don't ask somebody like a blog, because you'll get everybody's little, here, Science Daily. A study of hundreds of years of family trees suggested a man's genes play a role in him having sons or daughters. Men inherit a tendency to have more sons or more daughters from their parents. This means that a man with many brothers is more likely to have sons, while a man with many sisters is likely to have daughters. So that is Newcastle University, those limeys. Anyway, that's interesting. Research involved a study of 927 family trees containing information of 556,387 people from North America and Europe, going back to 1600. So it's the man. Probably has to do with the percentage of the different kinds of sperm that have one thing or the other. Okay. So you learned something new again. Okay, so this is another one. This is also theoretical probability. This is talking about genetics. So the question is, suppose a child is born with one cystic fibrosis carrier parent and one non-carrier parent. Find the probability of each of the following events. The child will have cystic fibrosis. The child will be a healthy cystic fibrosis carrier. The child will neither have nor carry the disease. So does anybody know the answer to this? What's the probability for the child having cystic fibrosis? Does anybody have? I have. Well, so here's a another little tidbit. So my daughter Jennifer, she was the one that had twins. So you have twins and you're over 30, they do genetic testing just to see what's going on. So she had genetic testing, and she found out that she was a carrier for cystic fibrosis. So her husband had the test done, and he came back as not being a carrier of cystic fibrosis. And they said, whew, we don't have to worry about it. Okay, so the answer is, in this case, the probability is 0 based on personal experience. But so you have, for a child to have cystic fibrosis, both parents have to be carriers, or one parent has to have cystic fibrosis, which is, less likely, unfortunately, because they tend not to live long enough to reproduce. At least, nowadays it's better, but so that means if she's a carrier, then either my wife or myself is a carrier. And cystic fibrosis is such a, it's not that common a disease that you may not experience it within your lifetime, your parents' life, your grandparents. It could be many generations back, and so you really don't know most of the time whether you are a carrier or not. So when my younger daughter was pregnant, she said, well, Jennifer's a carrier, so I could be a carrier. And she had the testing done, and she's a carrier as well. So what does that mean about our grandchildren? So we're going to ask her we're going to ask this question. But so the way you do that, if you've taken biology, you probably have seen this table. And what it consists of is, because the chances of being a carrier, if you are a carrier, that means you have a dominant gene and a recessive gene, and the recessive gene carries the disease. So the way you would look at it is, you would say, here's mom and here's dad, and there's different ways you're looking. So what we're going to do is we're going to look at uh, my case, and then we'll look at this case. So in this case, both of them are carriers. Um, so if my daughter found out that her husband was a carrier, then you have to make some decision. You have tough decisions to make. So carrier, or you have a lot of worry. Okay, so if the mother's a carrier, then there's one recessive gene, one dominant gene, and one recessive gene. If the dad is a carrier, then there is a dominant and recessive gene. And then when the eggs and sperm get together, it's just equally likely that they'll get one or the other from the parent, because you only get one of the genes. You don't get both genes. So you could get both dominant genes. That's the best scenario in this case. You could get the dominant gene from the mom and the recessive gene from the father. You could get the recessive gene from the mom and the dominant gene from the father, and then you get both recessive genes. And so this is the problem. If you get both recessive genes, then you have, this person has it. So this has cystic fibrosis. This person is going to be a carrier. This person is going to be a carrier. This person is not going to be a carrier at all. So this person's descendants are going to be free and clear for a while. So the probability, in this case, the sample space is 4. There are 4 possible results. This, that, that. The 4, say in this case, where they're both carriers, the probability, or the number of cases out of the 4 which have cystic fibrosis is 1. So the probability of having a child with cystic fibrosis when both of them are, both the parents are carriers, is going to be 1/4, which is pretty big. It's 25% chance. The number of cases where they're the carrier out of the 4 is 2. So the probability of the child being a carrier is going to be 2/4, which is a half. And the ones that is the best, where they don't have either one of them, that there's one of those cases. So the probability of the child being fine is 1/4. Okay, so those are the probabilities. Now, in this case, what you have is you have the same situation, except so we'll let the dad be the carrier here in this case. So there's dad, there's mom. So mom, because she's not a carrier, has 2 dominant genes, and the dad has a dominant gene and a recessive gene. So if you fill out the table, you've got R and R, you've got R and R, capital R, you've got capital R and small r, capital R and small r. So the answer to question 30 here, what's the probability of, in this scenario, of the child having cystic fibrosis, is 0. The probability of a child who will be healthy but a carrier will be 2 out of 4, because there's 2 of these out of 4. So that's 1/2. And that the child will neither carry nor have the disease is 2/4, which is a half. So this is probably what happened with my parents. One was a carrier, one was not. You get a 50% chance of passing it on. And the same thing happened with my wife and I, assuming, one of us is a carrier, So what'll happen is, because this is the case for my daughter, this is the case for my daughter, it's 50% chance their children will be a carrier. So they'll be tested. And then if they're positive, then you'll check. If they're not a carrier, then you don't have to do the father. I'm going to go ahead and assign the homework for this section, and then we'll finish for today. So that was about where I was with the other class. So Actually, I had a little more to talk about in the class, so it'll work out well. So this will be due next Tuesday. So remember the test, you can bring one sheet. If you haven't turned in your homeworks yet for Chapter 10, do that on Tuesday. For Rockbridge, every other person is going to have a different test, so don't cheat off the person next to you because you're going to get the wrong answer.